we had this before. We erased the numbers. And this time, we're given the derivative. So some of the things that we keep in mind when we're figuring this out, right? When we're figuring out an equation, what did we do? We found the derivative equals something. We set that derivative equal to 0, and we find our critical points. Our critical points are where that derivative is equal to 0. And in our example here, we have two places where our derivative is equal to 0. So what would we have done when we were graphing this? Well, we would have taken our derivative, set it equal to 0. The next thing we would have done is we would have checked which of these intervals are positive and which of them are negative by plugging a value into our equation. The problem is now we don't have an equation, but since we have the graph, we still know where things are positive and where they're negative. We're going to know that this section is negative, this section is positive, and this section is negative from this graph. Because in that first section, all of our y values are negative here. In this second section, all of our y values are positive, and the third section, they're all negative again. So what does that tell us about our original graph? Our original graph is decreasing, then increasing, then decreasing again. So those are some of the things that we can tell from this graph. Now, where those points are, we can't tell exactly where they are. Now, we know that it's going to have a local minimum at this first one and a local maximum at the other one. Since we have an x squared graph here, we know that our original graph is going to have to be an x cubed graph. And I'm going to put an idea down. I'm going to pick a random minimum here and a random maximum here, and I'm going to draw a curve going through there. Now, you might say, well, how do I know that's where the maximum is and that's where the minimum is? Why couldn't it be higher up or lower down? Well, the answer is it could be higher up or lower down. We're just going to get an approximate sketch of it. Now, the reason why I'm going to say it could be higher up and lower down is, let's say, now I don't know the equation of this x cubed graph, but let's say this x cubed graph that I just drew happens to be this. Okay? Now, we could take the derivative of that. The derivative, if this was y, the derivative would be 3x squared plus 4x plus 5. What would happen if I added a plus 7 to that? Okay? Nothing would happen to the derivative, but what would happen to the original function? Can you see that would be a horizontal shift 7 up? Okay? What happens if I put minus 7? That would shift it 7 down. So what I'm trying to show here is that as long as I have a minimum here and a maximum there, this graph, up or down, would still produce the same derivative graph, because that constant at the end is not going to affect my derivative graph. So that's why we're not able to graph it perfectly, because it could be any sort of graph, but there are key characteristics of the graph that we can show. And those key characteristics, we know there has to be a minimum here. We know there has to be a local maximum there. And because we have a quadratic function as our derivative, our function before that has to be an x cubed. So this gives us an idea of what that looks like. Now, if we were continuing, the next thing we would find would be our second derivative. And if we found our second derivative, we'd find out where things were concave up and concave down. Now, remember that our second derivative is just the first derivative of our first derivative. So we can either think of this x cubed graph and say, here's our second derivative. We make it equal to 0, and it's going to be equal to 0 at the place where it changes concavity. Now, if I'm thinking of the second derivative based on my original graph, I'm going to have a change in concavity, looks like right there. Does that make sense? If I think of my second derivative as the first derivative of my first derivative, then if I'm just doing a first derivative of my first derivative, so my blue graph here is my derivative. If I do the derivative of that, wherever I have a maximum, I'm going to have a 0. So this point where it's equal to 0 on my second derivative is going to be the same place that I have a maximum on my first derivative or a minimum on a first derivative. Do you notice how this maximum matches up with that inflection point? So these questions are hard because you're dealing with big concepts abstractly. We don't have the numbers to fall back on. We just have to think about them abstractly. So we know that it's going to be equal to 0 right there. Now, if we were doing our second derivative based on the original black graph, we would have found out that it's concave up here and concave down there. And you can see that from your black graph. Okay? And because you find that it's concave up here and concave down there, you would find out that it has to be positive here and negative there. So that would be the graph of our second derivative. The other thing you could think about here is here I have a parabola. What's the derivative of a parabola? A straight line. So it would make sense that our straight line would be here. How do I know the slope of my line goes down from left to right? If I just had my blue graph, my parabola here, can you see that your parabola is changing from increasing to decreasing at that maximum? And if it's increasing before, it has to be positive. So that's why this section of the graph is above the x-axis. And decreasing after would have to be negative. Yes, because if the parabola is facing down, you would have a negative x squared. And when you do the derivative of that, you're going to get a negative 2x. Of course, you could have any number in front of there, which would change it. But what we notice is our slope has to be a negative slope as a result. So there is a couple of different ways of looking at this. Sometimes you can think about, well, how did I do my graphing right from the beginning, going through my first derivative and my second derivative, and think my first derivative shows where things are increasing and decreasing. My second derivative shows concavity, and base everything on your first graph and think of it that way. The other thing you can do in this situation, starting with your derivative graph, is think that my second derivative is just my derivative of my first derivative of my first derivative. And then you can think of it that way. Here I have a parabola, so the derivative would be a line. Either way, the good thing to use as a shortcut throughout, well, what kind of graph? Here I have f prime as some sort of parabola. So that means if I did the derivative again, I would have some sort of line. And if I worked backwards, I would have some sort of x cubed graph to start from. And that can be very helpful just for getting an idea of what each of these graphs should look like.